Hey, good people, welcome back. This is the first of two short videos that I'd like you to watch this week. In this video, we're going to learn a technique called completing the square. And in the next video, we're going to apply that technique to graph a few quadratic equations. So just as a refresher, last week we looked at two special case polynomials, perfect square trinomials, and also something called difference of two squares. The perfect square trinomials are what we're going to focus on this week. And just as a refresher, here are a couple problems. How could you factor x squared plus 8x plus 16? Well, we learned that this has a special property where the middle term is twice the square root of the product of the leading term and the final term. So the square root of x squared is x, the square root of 16 is 4, and 2 times x times 4 is 8x, and that's what we have in the middle. So if it follows that format, it's incredibly easy to factor. You can just always take the square root of the first term, take the square root of the third term, and write those answers, and separate those two answers by whatever sign's in the middle. And there was a plus 8x, and we're going to put an x plus 4 there, and then this is squared. So if they're perfect square trinomials, again, incredibly easy to factor. You could just do the square root of that first term, the square root of the third term, separate those two answers with whatever sign's in the middle. So we have x squared plus 6x plus 9. We're going to put a x plus 3 in parentheses. The quantity x plus 3 squared is equal to x squared plus 6x plus 9. Another one, x squared plus 16x plus 64. We're just going to take the square root of x squared as x. The square root of 64 is 8, and there's a plus in the middle. We're going to separate by a plus. And you could check your work by actually foiling these, multiplying these binomials. This final one down here, x squared plus 16x plus 70, this is not a perfect square trinomial. The middle term is not equal to twice the product of the square root of the first and third terms. And there is a way to actually change this into a perfect square trinomial so you can factor it. But as it stands, this is not something we know how to factor. So we're going to have to come back to this problem in the next video. We have to learn a technique first to turn this into a perfect square trinomial. And that technique is called completing the square. It's called completing the square because it can be modeled really nicely geometrically. This algebraic process, we're going to kind of model it using algebra tiles. And just as an introduction to algebra tiles, here's like just an example of some polynomial multiplication using algebra tiles. So the algebra tiles are not necessary at all. It's really just to make this concept more concrete. What is the quantity x plus 3 squared? Well, hopefully you know how to get this answer. You would multiply it out. You would do x plus 3 times x plus 3 using the distributive property or using FOIL, first times first, outside times outside, inside times inside, last times the last, and you can get your answer there. But this also really can be modeled geometrically. In this picture here, we have this big blue square with edge length x that represents an x squared. This purple rectangle with short edge 3 and longer edge equal to x. If you find the area of that, 3 times x is 3x. Another one of those identical purple rectangles. And then this little red square down here that you can see has a height of 3 and a width of 3. That would be 9. If you added up this entire 4 shapes, you would have the area is equal to x squared plus 3x plus 3x plus 9, which is identical to what we saw up here, and it simplifies to x squared plus 6x plus 9. And another way to look at that is that the area of this entire big square here of edge length x plus 3 and another edge length of the same x plus 3 is equal to x squared plus 6x plus 9. If I'm confusing you by the shapes, I'm sorry. This is just trying to connect it to the reason they call this completing the square. Another quick example. If you wanted to get the answer to the quantity x plus 7 squared using algebra tiles, you could construct this diagram that I have here, and this is a square of edge length x plus 7. You can see that the edge is equal to x plus 7. So when you're doing x plus 7 squared, you're really just finding the area of this square, because the area of a square is the length times the width. And we can get that just by adding up these smaller components. The area of this blue square is x squared. The area of this purple rectangle is edge length x and height 7, 7 times x, 7x. An identical purple rectangle over here, 7x. And this red square, you can see that this distance is 7, and this distance is also 7. 7 times 7 is 49. So we have our answer. It's x squared plus 7x plus 7x plus 49, and that's x squared plus 14x plus 49. This is not necessary. This is just to help you see the reason why they call this completing the square. So what if you were trying to find, I don't know, the number that would make this x squared plus 6x plus blank? What number could I put in that blank that would make this into a perfect square trinomial? Well, if you saw this geometrically, it would probably be obvious what would have to go in here to make this a perfect square. Here's a geometric representation of the same thing. This is x squared. This is 3x plus 3x is 6x. So this is x squared plus 6x. And the question is, what would we have to put in here to make this add up to a perfect square? Well, you can see that this has an edge length of 3, and an area of it would be 3 times 3, which is 9. So that's our answer. The number that would have to go in here to make this a perfect square is 9. And do you see why they call this technique completing the square? We had this missing piece, and we had to fill in the gap to make this a nice perfect square. They call this technique completing the square. Now let's see how this 9 relates to the rest of the polynomial. The number that you put in here that completes the square has a relationship between the other two parts of the polynomial. It is related to these two parts. It happens to be half of this number squared. And you can kind of see that from the geometry down here. We took that 6 and we split it in half here and here. And then when you square that, you get this number. So if I had to fill in the missing number here to make this a perfect square, I would take half of this and I would square it. So the question is x squared plus 20x plus blank. To figure out the number that would turn that into a perfect square, we just need to take half of this number and square it. Half of 20 is equal to 10. 10 squared is 100. That would turn this into a perfect square trinomial. What number could I put here to make this a perfect square trinomial? X squared plus 14x plus blank. Well, half of 14 is 7. 7 squared is 49. That's what goes in there. What number can I put here to make this a perfect square trinomial? Half of negative 10 is negative 5. Negative 5 squared is 25. What number can I put here? Hopefully you figured it out. It is 169, because half of 26 is 13, and 13 squared is 169. And the number that goes here, if you want to try that on your own, you can go ahead, pause the video. Half of negative 16 is equal to negative 8, and negative 8 squared is positive 64. So the book has a nice little recipe for completing the square, and they give us this little formula right here. Here it is. It says to make a perfect square trinomial from a binomial of the form x squared plus bx, add the square of half of the coefficient of the x term. And that is a nice little formula you can use to complete the square. So this really wasn't the full story. The full story is how do we use this to our advantage? And that comes into play when we start to graph quadratics. Just like there was a good linear equation form that you guys were comfortable with, the slope-intercept form, y equals mx plus b, there's a really good form for graphing quadratics, graphing parabolas, and that's called the vertex form. So the linear equations were really easy to graph when we knew the slope and the y-intercept, and it turns out that parabolas are really easy to graph when we know their vertex. We're going to learn about that in the next video. Thank you for watching, and please click on to the next video.